Copper, a reddish-brown metal that lacks the sparkle of gold or silver, has never been seen as precious in the traditional sense. It doesn't sit behind glass displays or draw attention with its looks. And yet, it quietly powers nearly every part of our modern lives. It runs through the walls of our homes, hides inside circuit boards, drives motors, powers factories, moves trains, and even supports satellites orbiting far above the Earth. Its presence is everywhere, but its story is rarely told. Because before it becomes a wire carrying electricity or a coil in a machine, copper begins as nothing more than chunks of rock buried deep underground. The journey to transform those raw, lifeless stones into a metal that fuels the world is long, demanding, and often invisible to the very people who depend on it. In this video, we'll follow that journey. From the depths of the Earth to the heart of technology, you'll see why copper, though it doesn't shine, has become the nervous system of the modern world. Not many people realize it, but copper is the very first material to greet the sunrise atop the torch of the Statue of Liberty. That iconic green color isn't paint, it's a patina formed over time, a quiet reminder of how copper endures. For over a century, this unassuming metal has wrapped the idea of freedom in a cloak of timeless beauty. But its story stretches much farther back. In the heart of the ancient Aztec Empire, long before the 16th century, copper was more than just useful. It was sacred. The Aztecs shaped it into tools, ritual masks, and ceremonial weapons, treating it as a material of power and purpose. Today, copper doesn't stand in temples or on thrones, but it surrounds us more than ever. It lives inside our phones, powers electric vehicles, connects cities through vast electrical grids, and keeps factories running around the clock. Each year, over $200 billion worth of copper changes hands, making it a cornerstone of the global economy. And unlike many materials, copper can be recycled again and again without losing its quality, a trait that makes it not only practical, but vital for a sustainable future. The journey of copper begins deep underground, where layers of rock quietly guard a reddish-brown treasure. Hidden beneath the Earth's crust, sometimes hundreds of meters down, lie veins of copper-rich minerals like chalcopyrite, bornite, or malachite. Depending on how deep the ore is buried, miners choose the most suitable method, either extracting it from the surface or drilling down into the earth. For open-pit mines, the most common method today, the entire overlying layer of soil and rock is gradually removed in giant steps. Engineers drill hundreds of holes into the ore body, each 10 to 20 meters deep, using massive hydraulic rigs. These holes are then packed with industrial explosives and wired together through a precise electronic detonation system. Once everything is ready, a loud siren signals the blast. The detonation follows strict safety protocols, causing the rock to fracture in a controlled direction and breaking up thousands of tons of stone in a single event. Immediately after the blast, enormous tracked excavators with buckets as large as 40 cubic meters begin scooping up the debris. They load it onto ultra-heavy-duty trucks, some nearly 8 meters tall, each capable of hauling dozens of tons of material out of the mine. Layer by layer, the copper-rich rock is stripped and carried away. But when the ore lies deeper, miners build an underground tunnel system, interwoven like a network of arteries beneath the earth to reach the core deposit. There, the cycle of drilling, blasting, loading, and hauling continues in tighter, more complex spaces, demanding even greater precision and skill. Not all copper comes from deep underground mines. In reality, more than 30% of the copper used globally each year is sourced through recycling, turning discarded materials into something valuable once again. Unlike many other substances, copper can be recycled endlessly without losing its electrical conductivity or purity. Old wiring, broken electronics, plumbing pipes, motor casings, all of these can be collected, sorted, and sent back into the furnace. At recycling plants, scrap copper is melted at temperatures exceeding 1,000 degrees Celsius to remove impurities. The purified metal is then cast into new billets, ready for an entirely new life cycle. This process consumes far less energy than mining and refining raw copper, reducing CO2 emissions and easing pressure on the planet's natural resources. Recycling isn't just about extending the life of a durable metal. It's a quiet reminder that not every treasure needs to be dug from the earth. Sometimes it's already in our hands, simply waiting for a second chance. Once brought to the surface, the copper ore is transported by ultra-heavy-duty trucks to a processing plant located a few kilometers from the mine. The refining journey begins with primary crushing, where massive rocks, some the size of dining tables, are broken down into fragments smaller than 20 centimeters. At the heart of this stage is a jaw crusher with two steel plates, one fixed, one moving, that exert a crushing force of up to 250 megapascals, equal to the pressure at the bottom of the ocean. The ore is loaded from a 100-ton feed hopper, dropped onto a vibrating conveyor, and funneled into the crushing chamber. Here, the system handles between 1,000 and 1,500 tons of material per hour. Despite the scale and force involved, the entire process is monitored and controlled automatically. Sensors track pressure, sound, and vibration levels, acting like silent electronic senses that detect unwanted materials and protect the machinery from damage. After passing through the primary crushing stage at the mine, the copper ore, now reduced to pieces smaller than 20 centimeters, is loaded onto conveyor belts or specialized transport trucks and sent to the main concentration plant. At many modern copper mining and processing complexes, ore that has undergone primary crushing is transported via conveyor systems stretching several kilometers, directly linking the mine to the concentration plant. These massive belts are among the most iconic pieces of infrastructure in the mining industry. A continuous mechanical flow that runs day and night, carrying raw material across mountain slopes and rugged terrain. This is where the real refining process begins. At the processing plant, the ore enters the fine grinding stage, where its size is reduced to an almost powder-like form. The core of this operation is the ball mill, a massive cylindrical machine, over 10 meters long, resembling a giant horizontal steel drum spinning endlessly. Inside, hundreds of steel balls, each about the size of an orange, rotate with immense weight and force. With every spin, these balls collide with the ore, generating intense pressure and friction that gradually crush the rock into particles smaller than 0.075 millimeters, about 3 times thinner than a human hair. The entire process is closely monitored by sensors that track temperature, vibration, and rotational speed. These data points are constantly analyzed to adjust grinding conditions based on the type of ore being processed, ensuring peak performance and maximum efficiency. After being ground into fine powder, the copper ore moves into the flotation system, a critical step designed to separate copper particles from the surrounding waste rock. This process takes place inside massive flotation tanks filled with a slurry of mineral powder, water, and a small amount of collectors, special chemicals that selectively attach to the surface of copper-bearing particles. From the bottom of the tank, air compressors continuously pump up millions of tiny bubbles. As they rise through the slurry, these bubbles attach to the copper-rich particles, thanks to the collector chemicals, and carry them to the surface. There, they form a dense, shimmering froth, rich in metal and smooth like whipped cream. Meanwhile, heavier particles like sand, clay, and crushed rock, which don't react with the bubbles, quietly settle at the bottom. A rotating mechanical arm gently skims the froth from the surface, guiding it into a concentrated stream of copper cream. Each tank can handle up to 1,000 cubic meters of slurry per hour, the equivalent of nearly 20 family-sized swimming pools in constant motion. The entire system runs automatically, and even small shifts in airflow, chemical balance, or temperature can significantly affect how efficiently the copper is recovered. Even after being separated from the rock and concentrated, copper is still not ready for practical use. To turn it into usable metal, it must go through smelting, a high-temperature process where fire, air, and chemistry work together to strip away the mineral shell and release the metal hidden inside. The copper concentrate from flotation, usually containing about 30 to 40% copper, is fed into smelters, massive industrial furnaces that can stretch dozens of meters and reach temperatures up to 1,1200 degrees Celsius, hotter than volcanic lava. Inside, the material is heated together with silica and other additives, which help remove impurities. Elements like iron react with the silica to form a lighter, molten slag that floats to the surface, much like foam on a boiling pot of soup, while the denser molten copper settles at the bottom, dark and heavy like thick syrup. The result is what's known as blister copper, named for its rough, blistered surface as it solidifies. At this stage, it reaches around 98% purity and is suitable for certain industrial uses, though not yet ready for applications requiring high conductivity or refined finish. Before moving on to the next stages of processing, blister copper must be reheated in specialized annealing furnaces. This step helps stabilize the metal's internal structure, ensuring the copper heats evenly from within and relieving any residual stress left from solidification. Under the glow of intense red flames, the massive slabs of copper gradually become more pliable, softened, and prepared for the final phase of refining. After being reheated and cooled, the blister copper slabs move on to their final transformation, electrolytic refining. In massive tanks, filled with a solution of copper sulfate and sulfuric acid, the crude copper anodes are suspended alternately with stainless steel cathode plates. When a direct current is applied, copper from the anodes dissolves into the solution, then migrates and recrystallizes onto the surface of the cathodes, forming a layer of copper that is almost perfectly pure. This process takes between 7 and 10 days. The result is thin, flat cathode sheets with a purity of up to 99.99%, the gold standard for copper used in electrical wiring, electronics, and high-tech industries. It's this form of copper that powers our homes, our phones, and the world around us, even though we rarely see it. Once electrolytic refining is complete, the copper is ready for its next transformation. With unmatched purity, it enters the shaping phase, beginning a new chapter as wires, circuit boards, or critical industrial components. At the wire manufacturing plant, copper enters the shaping phase, where the metal is stretched, thinned, and prepared to become an electrical conductor. Copper billets are first passed through hot rolling mills to gradually reduce their thickness. Then they move on to cold drawing machines, pulled through a series of dies with increasingly smaller diameters. With each pass, the wire becomes thinner and longer, eventually reaching diameters of just a few millimeters. Throughout the drawing process, the copper must be annealed under carefully controlled temperatures to maintain flexibility and prevent cracking. Once the desired thickness is achieved, the wire is coated with insulation if intended for electrical use, then wound into large coils, each weighing several hundred kilograms. From here, the finished copper wires are ready to be cut, spliced, and installed across every sector, from household wiring and high-voltage power cables to the microscale circuits inside electronic devices. In South Korea, copper craftsmanship has a history spanning thousands of years, dating back to the Three Kingdoms period, around the 1st century BCE. From early on, Koreans developed techniques to smelt copper and cast temple bells, incense burners, Buddha statues, and ceremonial objects, blending refined craftsmanship with deep spiritual belief. One of the most distinctive traditions is bangjayugi, a unique method of hand-forging bronze, where a copper tin alloy is melted, roughly cast, and then repeatedly heated, hammered, and rolled by hand until it reaches its final form. This technique not only produces durable, highly heat-conductive cookware, but also gives the metal a warm golden sheen, a quality Koreans associate with prosperity, cleanliness, and purity. Today, bangjayugi is recognized as an official national intangible cultural heritage, and handmade bronzeware continues to be valued in many traditional Korean households. In Korean culture, bronze items are more than just everyday tools. They are seen as a living link between past and present. Each hammer mark, each subtle pattern carved into the surface, carries the imprint of tradition and reflects a deep reverence for ancestors. These handcrafted objects are not only practical but also symbolic, preserving the spirit of heritage through form, function, and craftsmanship. From anonymous chunks of ore buried deep underground to the fine copper wires that carry electricity around the world, every kilogram of copper is the result of a long, complex process involving advanced technology, precise control, and relentless human effort. What may seem like a straightforward task actually hides a system of automation, chemical reactions, and calculations, fine-tuned down to every air bubble and fraction of a pH level. Thank you for joining us in exploring a metal that feels familiar, yet is rarely understood in full. Copper isn't just found in wires or circuit boards. It's a symbol of how humans have learned to shape raw materials into the foundation of modern life. Because behind every familiar material lies a remarkable journey, where technology, people, and nature come together in ways we don't always see. If this video gave you a new perspective on this quiet but essential metal, don't forget to like and subscribe to keep following along with us.